Hello, this is Teacher Todd. We're in Network Security Essentials, and we're on to Chapter 12, Firewalls. The need for firewalls. Information systems in corporations, government agencies, and other organizations have undergone a steady evolution. The following are notable developments. First, we had centralized data processing systems with a central mainframe supporting a number of terminals which were directly connected. Local area networks, LANs, interconnecting PCs and terminals to each other and the mainframe. Then premises networks, consisting of a number of local area networks, interconnecting PCs, servers, and perhaps a mainframe or two. Enterprise-wide network, consisting of multiple geographically distributed premises networks interconnected by a private wide area network, WAN. Internet connectivity, in which the various premises networks all hook to the internet and may or may not be connected by a private WAN. Internet connectivity is no longer optional for organizations. The information and services available are essential to the organization. Moreover, the individual users within the organization want and need internet access, and if this is not provided via their LAN, they will use dial-up capability from their PC to an internet service provider, ISP. However, while internet access provides benefits to the organization, it enables the outside world to reach and interact with local area network assets. This creates a threat to the organization. While it is possible to equip each workstation and server on the premise network with strong security features, such as intrusion protection, this may not be sufficient and in some cases is not cost effective. Consider a network with hundreds or even thousands of systems running various operating systems, such as different versions of Unix and Windows. When a security flaw is discovered, each potentially affected system must be upgraded to fix that flaw. This requires scalable configuration management and aggressive patching to function effectively. While difficult, this is possible and is necessary if only host-based security is used. A widely accepted alternative, or at least complement to host-based security services, is the firewall. The firewall is inserted between the premises network and the internet to establish a controlled link and to erect an outer security wall or perimeter. The aim of this perimeter is to protect the premises network from internet-based attacks and to provide a single choke point where security and auditing can be imposed. The firewall may be a single computer system or a set of two or more systems that cooperate to perform the firewall function. The firewall then provides an additional layer of defense, insulating the internal systems from external networks. This follows the classic military doctrine of defense in depth, which is just as applicable to IT security. Firewall characteristics. Here's a list of some design goals for a firewall. 1. All traffic from inside to outside and vice versa must pass through the firewall. This is achieved by physically blocking all access to the local network except via the firewall. Various configurations are possible, as explained later in this chapter. 2. Only authorized traffic, as defined by the local security policy, will be allowed to pass. Various types of firewalls are used, which implement various types of security policies, as explained later in this chapter. 3. The firewall itself is immune to penetration. This implies the use of a hardened system with a secured operating system. Trusted computer systems are suitable for hosting a firewall and often required in government applications. A critical component in the planning and implementation of a firewall is to specify a suitable access policy. This lists the types of traffic authorized to pass through the firewall, including address ranges, protocols, applications, and content types. This policy should be developed from the organization's information security risk assessment and policy. This policy should be developed from a broad specification of which traffic types the organization needs to support. It is then refined to detail the filter elements we discuss next, which can then be implemented within an appropriate firewall topology. SP 800-41-1, Guidelines on Firewalls and Firewall Policy. This lists a range of characteristics that a firewall access policy could use to filter traffic, including IP address and protocol values, controls access based on the source or destination addresses and port numbers, direction of flow being inbound or outbound, and other network and transport layer characteristics. This type of filtering is used by packet filter and stateful inspection firewalls. It is typically used to limit access to specific services. Application protocol controls access on the basis of authorized application protocol data. This type of filtering is used by an application level gateway that relays and monitors the exchange of information for specific application protocols. For example, checking SMTP email for spam or HTTP web requests to authorized sites only. User identity controls access based on the user's identity, typically for inside users who identify themselves using some form of secure authentication technology, such as IPsec. Network activity controls access based on considerations such as the time of request, for example, only during business hours, rate of requests, for example, to detect scanning attempts, or other activity patterns. Firewall expectations. Before proceeding to the details of firewall types and configurations, it is best to summarize what one can expect from a firewall. The following capabilities are within the scope of a firewall. 1. A firewall defines a single choke point that keeps unauthorized users out of the protected network, prohibits potentially vulnerable services from entering or leaving the network, and provides protection from various kinds of IP spoofing and routing attacks. The use of a single choke point simplifies security management because security capabilities are consolidated on a single system or set of systems. 2. A firewall provides a location for monitoring security-related events. Audits and alarms can be implemented on the firewall system. 3. A firewall is a convenient platform for several internet functions that are not security related. These include a network address translator, which maps local addresses to internet addresses, and a network management function that audits or logs internet usage. 4. A firewall can serve as the platform for IPsec. Using the tunnel mode capability described in Chapter 9, the firewall can be used to implement virtual private networks. Firewall limitations. Firewalls do have their limitations, including the following. 1. The firewall cannot protect against attacks that bypass the firewall. Internal systems may have dial-out capability to connect to an ISP. An internal LAN may support a modem pool that provides dial-in capability for traveling employees and telecommuters, or they may use their SIM cards. 2. The firewall may not protect fully against internal threats, such as disgruntled employee or an employee who unwittingly cooperates with an external attacker. 3. An improperly secured wireless LAN may be accessed from outside the organization. An internal firewall that separates portions of an enterprise network cannot guard against wireless communications between local systems on different sides of the internal firewall. 4. A laptop, PDA, or portable storage device may be used and infected outside the corporate network and then attached and used internally. Types of firewall. A packet filtering firewall applies a set of rules to each incoming and outgoing IP packet and then forwards or discards the packets, as shown in the figure 12.1b. The firewall is typically configured to filter packets going in both directions, from and to the internal network. Filtering rules are based on information contained in a network packet. Source IP address. The IP address of the system that originated the IP packet. For example, 192.168.1.1. Destination IP address. The IP address of the system the IP packet is trying to reach. For example, 192.168.1.2. Source and destination transport level address. The transport level, for example, TCP or UDP, port number, which defines applications such as SNMP or Telnet. IP protocol field defines the transport protocol. Interface. For a firewall with 3 or more ports, which interface of the firewall the packet came from, or which interface of the firewall the packet is destined for. The packet filter is typically set up as a list of rules based on matches to fields in the IP or TCP header. If there is a match to one of the rules, that rule is invoked to determine whether to forward or discard the packet. If there is no match to any rule, then a default action is taken. 2 default policies are possible. Default discard. That which is not expressly permitted is prohibited. Default forward. That which is not expressly prohibited is permitted. The default discard policy is more conservative. Initially, everything is blocked and services must be added on a case-by-case basis. This policy is more visible to users who are more likely to see the firewall as a hindrance. However, this is the policy likely to be preferred by businesses and government organizations. Further, visibility to users diminishes as rules are created. The default forward policy increases ease of use for users, but provides reduced security. The security administrator must, in essence, react to each new security threat as it becomes known. This policy may be used by generally more open organizations, such as universities. Packet filtering example. The table is a simplified example of a rule set for SMTP traffic. The goal is to allow inbound and outbound email traffic, but to block all other traffic. The rules are applied top to bottom to each packet. A. Inbound mail from an external source is allowed. Port 25 is for SMTP incoming. B. This rule is intended to allow a response to an inbound SMTP connection. C. Outbound mail to an external source is allowed. D. This rule is intended to allow a response to an inbound SMTP connection. E. This is an explicit statement of the default policy. All rule sets include this rule implicitly as the last rule. Packet filtering firewalls. One advantage of a packet filtering firewall is its simplicity. Also, packet filters typically are transparent to users and are very fast. This lists the following weaknesses of packet filter firewalls. Because packet filter firewalls do not examine upper layer data, they cannot prevent attacks that employ application-specific vulnerabilities or functions. For example, a packet filter firewall cannot block specific application commands. If a packet filter firewall allows a given application, all functions available within that application will be permitted. Because of the limited information available to the firewall, the logging functionality present in packet filtering firewalls is limited. Packet filter logs normally contain the same information used to make access control decisions: source address, destination address, and traffic type. Most packet filter firewalls do not support advanced user authentication schemes. Once again, this limitation is mostly due to the lack of upper layer functionality by the firewall. Packet filter firewalls are generally vulnerable to attacks and exploits that take advantage of problems within the TCP/IP specification and protocol stack, such as network layer address spoofing. Many packet filter firewalls cannot detect a network packet in which the OSI layer 3 addressing information has been altered. Spoofing attacks are generally employed by intruders to bypass the security controls implemented in a firewall platform. Finally, due to the small number of variables used in access control decisions, packet filter firewalls are susceptible to security breaches caused by improper configurations. In other words, it is easy to accidentally configure a packet filter firewall to allow traffic types, sources, and destinations that should be denied based on an organization's information security policy. Attacks and countermeasures. Some of the attacks that can be made on a packet filtering firewall and the appropriate countermeasures are the following. IP address spoofing. The intruder transmits packets from the outside with a source IP address field containing an address of an internal host. The attacker hopes that the use of a spoofed address will allow penetration of systems that simply employ source address security, in which packets from specific trusted internal hosts are accepted. The countermeasure is to discard packets with an inside source address if the packet arrives on an external interface. In fact, this countermeasure is often implemented at the router external to the firewall. Source routing attacks. The source station specifies the route that a packet should take as it crosses the internet, in the hopes that this will bypass security measures that do not analyze the source routing information. The countermeasure is to discard all packets that use this option. Tiny fragment attacks. The intruder uses the IP fragmentation option to create extremely small fragments and force the TCP header information into a separate packet fragment. This attack is designed to circumvent filtering rules that depend on TCP header information. Typically, a packet filter will make a filtering decision on the first fragment of the packet. All subsequent fragments of that packet are filtered out solely on the basis that they are part of the packet whose first fragment was rejected. The attacker hopes that the filtering firewall examines only the first fragment and that the remaining fragments are passed through. A tiny fragment attack can be defeated by enforcing a rule that the first fragment of a packet must contain a predefined minimum amount of the transport header. If the first fragment is rejected, the filter can remember the packet and discard all subsequent fragments. Example stateful firewall connection state table. A stateful inspection packet firewall tightens up the rules for TCP traffic by creating a directory of outbound TCP connections as shown in the table. There is an entry for each currently established connection. The packet filter will now allow incoming traffic to high-numbered ports only for those packets that fit the profile of one of the entries in this directory. A stateful packet inspection firewall reviews the same packet information as a packet filtering firewall, but also records information about the TCP connections. Some stateful firewalls also keep track of the TCP sequence numbers to prevent attacks that depend on the sequence number, such as session hijacking. Some even inspect limited amounts of application data for some well-known protocols like FTP, IM, and SIPS commands in order to identify and track related connections. Application level gateway. An application level gateway, also called an application proxy, acts as a relay of application level traffic. The user contacts the gateway using a TCP/IP application, such as Telnet or FTP, and the gateway asks the user for the name of the remote host to be accessed. When the user responds and provides a valid user ID and authentication information, the gateway contacts the application on the remote host and relays TCP segments containing the application data between the two endpoints. If the gateway does not implement the proxy code for a specific application, the service is not supported and cannot be forwarded across the firewall. Further, the gateway can be configured to support only specific features of an application that the network administrator considers acceptable while denying all other features. Application-level gateways tend to be more secure than packet filters. Rather than trying to deal with the numerous possible combinations that are to be allowed and forbidden at the TCP and IP level, the application-level gateway need only scrutinize a few allowable applications. In addition, it is easy to log and audit all incoming traffic at the application level. A prime disadvantage of this type of gateway is the additional processing overhead on each connection. In effect, there are two spliced connections between the end users, with the gateway as the splice point, and the gateway must examine and forward all traffic in both directions. Circuit level gateway. A fourth type of firewall is the circuit level gateway or circuit level proxy. This can be a standalone system, or it can be a specialized function performed by an application level gateway for certain applications. As with an application gateway, a circuit level gateway does not permit an end-to-end TCP connection. Rather, the gateway sets up two TCP connections, one between itself and a TCP user on the inner host, and one between itself and a TCP user on an outside host. Once the two connections are established, the gateway typically relays TCP segments from one connection to the other without examining the contents. The security function consists of determining which connections will be allowed. A typical use of circuit level gateways is a situation in which the system administrator trusts the internal users. The gateway can be configured to support application level or proxy service on inbound connections and circuit level functions for outbound connections. In this configuration, the gateway can incur the processing overhead of examining incoming application data for forbidden functions, but does not incur that overhead on outgoing data. An example of a circuit level gateway implementation is the SOX package. Version 5 of SOX is specified in RFC 1928. The RFC defines SOX in the following fashion. The protocol described here is designed to provide a framework for client-server applications in both the TCP and UDP domains to conveniently and securely use the services of a network firewall. The protocol is conceptually a shim layer between the application layer and the transport layer, and as such does not provide network layer gateway services, such as forwarding of ICMP messages. SOX consists of the following components. The SOX server, which often runs on a Unix-based firewall or Linux. SOX is also implemented on Windows systems. The SOX client library, which runs on internal hosts protected by the firewall. SOXified versions of several standard client programs, such as FTP and Telnet. The implementation of the SOX protocol typically involves either the recompilation or relinking of TCP-based client applications, or the use of alternative dynamically loaded libraries to use the appropriate encapsulation routines in the SOX library. When a TCP-based client wishes to establish a connection to an object that is reachable only via a firewall, such determination is left up to the implementation. It must open a TCP connection to the appropriate SOCKS port on the SOCKS server system. The SOCKS service is located on TCP port 1080. If the connection request succeeds, the client enters a negotiation for the authentication method to be used, authenticates with the chosen method, and then sends a relay request. The SOCKS server evaluates the request and either establishes an appropriate connection or denies it. UDP exchanges are handled in a similar fashion. In essence, a TCP connection is opened to authenticate a user to send and receive UDP segments, and the UDP segments are forwarded as long as the TCP connection is open. Bastion host. A Bastion host is a system identified by the firewall administrator as a critical strong point in the network security. Typically, the Bastion host serves as a platform for an application level or circuit level gateway. Common characteristics of a Bastion host are as follows. The Bastion host hardware platform executes a secure version of its operating system, making it a hardened system. Only the services that the network administrator considers essential are installed on the Bastion host. These could include proxy applications for DNS, FTP, HTTP, and SMTP. The Bastion host may require additional authentication before a user is allowed access to the proxy services. In addition, each proxy service may require its own authentication before granting user access. Each proxy is configured to support only a subset of the standard applications command set. Each proxy is configured to allow access only to specific host systems. This means that the limited command feature set may be applied only to a subset of systems on the protected network. Each proxy maintains detailed audit information by logging all traffic, each connection, and the duration of each connection. The audit log is an essential tool for discovering and terminating intruder attacks. Each proxy module is a very small software package specifically designed for network security. Because of its relative simplicity, it is easier to check such modules for security flaws. For example, a typical Unix or Linux mail application may contain over 20,000 lines of code, while a mail proxy may contain fewer than 1,000. Each proxy is independent of other proxies on the Bastion host. If there is a problem with the operation of any proxy, or if a future vulnerability is discovered, it can be uninstalled without affecting the operation of the other proxy applications. Also, if the user population requires support for a new service, the network administrator can easily install the required proxy on the Bastion host. A proxy generally performs no disk access other than to read its initial configuration file. Hence, the portions of the file system containing executable code can be made read-only. This makes it difficult for an intruder to install Trojan horse sniffers or other dangerous files on the Bastion host. Each proxy runs as a non-privileged user in a private and secure directory on the Bastion host. Host-based firewall. A host-based firewall is a software module used to secure an individual host. Such modules are available in many operating systems or can be provided as an add-on package. Like conventional standalone firewalls, host-resident firewalls filter and restrict the flow of packets. A common location for such firewalls is a server. There are several advantages to the use of a server-based or workstation-based firewall. Filtering rules can be tailored to the host environment. Specific corporate security policies for servers can be implemented with different filters for servers used for different applications. Protection is provided independent of topology. Thus, both internal and external attacks must pass through the firewall. Used in conjunction with standalone firewalls, the host-based firewall provides an additional layer of protection. A new type of server can be added to the network with its own firewall without the necessity of altering the network firewall configuration. Personal firewall. A personal firewall controls the traffic between a personal computer or workstation on one side and the internet or enterprise network on the other side. Personal firewall functionality can be used in the home environment and on the corporate intranets. Typically, the personal firewall is a software module on the personal computer. In a home environment with multiple computers connected to the internet, firewall functionality can also be housed in a router that connects all of the home computers to a DSL, cable modem, or other internet interface. Personal firewalls are typically much less complex than either server-based firewalls or standalone firewalls. The primary role of the personal firewall is to deny unauthorized remote access to the computer. The firewall can also monitor outgoing activity in an attempt to detect and block worms and other malware. Example firewall configuration. The figure suggests the most common distinction, that between an internal and an external firewall. An external firewall is placed on the edge of a local or enterprise network, just inside the boundary router that connects to the internet or some wider network. One or more internal firewalls protect the bulk of the enterprise network. Between these two types of firewalls are one or more network devices in a region referred to as a DMZ, demilitarized zone. Network. Systems that are externally accessible but need some protections are usually located on the DMZ networks. Typically, the systems in the DMZ require or foster external connectivity, such as a corporate website, an email server, or a DNS server. The external firewall provides a measure of access control and protection for the DMZ systems consistent with their need for external connectivity. The external firewall also provides a basic level of protection for the remainder of the enterprise network. In this type of configuration, internal firewalls serve three purposes. 1. The internal firewall adds more stringent filtering capability compared to the external firewall in order to protect enterprise servers and workstations from external attack. 2. The internal firewall provides two-way protection with respect to the DMZ. First, the internal firewall protects the remainder of the network from attacks launched from DMZ systems. Such attacks might originate from worms, rootkits, bots, or other malware lodged in a DMZ system. Second, an internal firewall can protect the DMZ systems from attack from the internal protected network. 3. Multiple internal firewalls can be used to protect portions of the internal network from each other. For example, firewalls can be configured so that internal servers are protected from internal workstations and vice versa. A common practice is to place the DMZ on a different network interface on the external firewall from that used to access the internal networks. A VPN security scenario. In today's distributed computing environment, the Virtual Private Network, VPN, offers an attractive solution to network managers. In essence, a VPN consists of a set of computers that interconnect by means of a relatively unsecure network and that make use of encryption and special protocols to provide security. At each corporate site, workstations, servers, and databases are linked by one or more local area networks, LANs. The internet or some other public network can be used to interconnect sites, providing cost savings over the use of a private network and offloading the wider network management task to the public network provider. That same public network provides an access path for telecommuters and other mobile employees to log on to the corporate systems from the remote sites. But the manager faces a fundamental requirement: security. Use of a public network exposes corporate traffic to eavesdropping and provides an entry point for unauthorized users. To counter this problem, a VPN is needed. In essence, a VPN uses encryption and authentication in the lower protocol layers to provide a secure connection through an otherwise insecure network, typically the internet. VPNs are generally cheaper than real private networks using private lines, but rely on having the same encryption and authentication system at both sides. The encryption may be performed by firewall software or possibly by routers. The most common protocol mechanism used for this purpose is at the IP level and is known as IPsec. In the figure, we have a typical scenario of IPsec usage. An organization maintains LANs at dispersed locations. Non-secure IP traffic is conducted on each LAN. For traffic off-site through some sort of private or public WAN, IPsec protocols are used. These protocols operate in networking devices such as a router or firewall that connect each LAN to the outside world. The IPsec networking device will typically encrypt and compress all traffic going into the WAN and decrypt and uncompress traffic coming from the WAN. Authentication may also be provided. These operations are transparent to workstations and servers on the LAN. Secure transmission is also possible with individual users who dial into the WAN or connect in another way. Such user workstations must implement the IPsec protocols to provide security. They must also implement high levels of host security as they are directly connected to the wider internet. This makes them an attractive target for attackers attempting to access the corporate network. A logical means of implementing an IPsec is in a firewall, as shown in the figure. If IPsec is implemented in a separate box behind, internal to, the firewall, then VPN traffic passing through the firewall in both directions is encrypted. In this case, the firewall is unable to perform its filtering function or other security functions, such as access control, logging, or scanning for viruses. IPsec could be implemented in the boundary router outside the firewall. However, this device is likely to be less secure than the firewall and thus less desirable as an IPsec platform. Example, distributed firewall configuration. A distributed firewall configuration involves standalone firewall devices plus host-based firewalls working together under a central administrative control. The figure suggests a distributed firewall configuration. Administrators can configure host resident firewalls on hundreds of servers and workstations, as well as configure personal firewalls on local and remote user systems. Tools let the network administrator set policies and monitor security across the entire network. These firewalls protect against internal attacks and provide protection tailored to specific machines and applications. Standalone firewalls provide global protection, including internal firewalls and an external firewall, as discussed previously. With distributed firewalls, it may make sense to establish both an internal and an external DMZ. Web servers that need less protection because they have less critical information on them could be placed on an external DMZ outside the external firewall. What protection is needed is provided by host-based firewalls on these servers. An important aspect of a distributed firewall configuration is security monitoring. Such monitoring typically includes a log aggregation and analysis, firewall statistics, and fine-grained remote monitoring of individual hosts, if needed. Summary of firewall locations and topologies. We can now summarize the discussion from the sections to define a spectrum of firewall locations and topologies. The following alternatives can be identified. Host resident firewall. This category includes personal firewall software and firewall software on servers. Such firewalls can be used alone or as part of an in-depth firewall deployment. Screening router. A single router between internal and external networks with stateless or full packet filtering. This arrangement is typical for small office, home office applications. Single bastion inline. A single firewall device between an internal and external router. The firewall may implement stateful filters and/or application proxies. This is the typical firewall appliance configuration for small to medium-sized organizations. Single bastion T, similar to single bastion inline, but has a third network interface on bastion to a DMZ where externally visible servers are placed. Again, this is a common appliance configuration for medium to large organizations. Double bastion inline illustrates this configuration where the DMZ is sandwiched between bastion firewalls. This configuration is common for large businesses and government organizations. Double bastion T. The DMZ is on a separate network interface on the bastion firewall. This configuration is also common for large businesses and government organizations and may be required. For example, this configuration is required for the Australian government use. Distributed firewall configuration. This configuration is used by some large businesses and government organizations. Summary. Well, we've talked about the need for firewalls, the characteristics, access policies. We've talked about various types of firewalls. And we've talked about the bastion host and the host and personal firewalls. And we've shown you different topologies where you can place the firewalls in different locations and configurations. Well, thanks for listening from Teacher Todd.